All right, let's dive in. Today, we're going to crack open one of the most fundamental building blocks in all of electronics, the operational amplifier, or as you probably know it, the op-amp. Now, it might seem like some kind of mysterious black box, right? But what if I told you we could understand the whole thing by breaking it down into just 4 simple stages? We're going to follow a signal's journey right through it.
Yep, that's it. Just 4. The entire magic of an op-amp, this tiny little chip that powers, well, so much of our modern world, it really just comes down to following a signal as it moves through 4 very distinct, very logical stages.
Okay, so let's get right to the heart of what this thing is. At its core, an op-amp is a high-gain voltage amplifier. What does that mean? It means its entire job, its whole reason for being, is to take a teeny tiny difference in voltage between its 2 inputs and make that difference absolutely massive. And at one simple, powerful function, it makes it the backbone of, well, almost everything, from your stereo system to industrial control systems.
So to really get a feel for this, we're going to follow an electrical signal on its journey. Think of it like we're tagging along with it, from the second it walks in the door of the op-amp to the moment it leaves, totally transformed and ready to do some real work in a circuit.
And our journey starts right here. Stage 1, we're calling it the first handshake. This is basically the op-amp's front door. It's where the signal makes its grand entrance and gets its marching orders.
So what's its purpose? It's actually really simple. It looks at 2 incoming signals, it compares them, and then it amplifies only the difference between them. That's it, seriously. That single act of comparison is why the op-amp is such a game changer.
Now, this stage is a master multitasker. First off, it has a really high input resistance. Think of it like a polite listener. It takes in the signal without draining any power from the source. It doesn't mess with what it's connected to. Second, this is where most of the heavy lifting happens. I mean, the lion's share of the op-amp's voltage gain comes from right here. And how does it do all this? Well, it uses a clever little circuit called a differential amplifier, which is basically designed to be super picky. It ignores anything the 2 inputs have in common and zooms in only on what's different.
And those 2 inputs, you can think of them as 2 different doors. If our signal goes in the inverting input, the -1, it gets flipped upside down at the output. If it goes in the non-inverting input, the +1, it keeps its original shape. All the while, the op-amp is just constantly calculating the difference between those 2, and that calculation is the foundation for everything else that's about to happen.
All right, on to stage 2, the power boost. So our signal made it through the front door, it got its first big amplification, but we're not done yet. Oh no! Now it's time to really crank things up a notch.
And the purpose of this stage? It's super straightforward. Take the already amplified signal from stage 1 and give it another massive boost. It's like a second stage rocket kicking in, just pushing that signal's voltage gain even higher.
So really, this stage just builds on what the first one started. It takes that amplified difference and it boosts it again, sometimes even using another differential amplifier to do it. This is how we get that truly massive overall gain that op-amps are famous for. And all this power-up is to get the signal ready for a really crucial adjustment that's coming up next.
Which brings us neatly to stage 3, the level shift. Okay, so our signal is super powerful now, but it's not quite right. It needs a little bit of, let's say, calibration before it's ready for prime time.
See, this stage is all about correction. All that massive amplification in the first 2 stages, it tends to push the signal's baseline, its DC level, off-center. So the one and only job of this stage is to get rid of that unwanted DC offset and pull the whole signal right back down so it's perfectly centered around 0 volts or ground.
And this is absolutely vital. I mean, without this recentering step, the final output would just be wrong. This stage makes sure that if there's no difference between the inputs, there's 0 output. Simple as that. It often does this with a really efficient circuit called an emitter follower. You can think of it like a translator that perfectly matches the voltage, shifting the level down without messing with the actual amplified signal riding on top of it.
And here we are. We've reached the final leg of the internal journey. Stage 4, the final push. Our signal is now perfectly amplified and perfectly calibrated. Now it just needs the muscle to go out into the real world and actually do something. Like drive a speaker or spin a motor.
Now this last stage is different. It's not about amplifying the voltage anymore. Nope. This stage is all about current. Its whole job is to be a buffer, to be able to push a whole lot of current into whatever device it's connected to, what we call the load, without the signal's voltage just collapsing under the pressure.
And to get this kind of power, the output stage is designed with incredibly low resistance, which you'll notice is the exact opposite of the input stage. This is what lets it deliver big bursts of current whenever they're needed. And it does this super efficiently using something called a push-pull amplifier. It's just like it sounds. Two transistors work as a team. One pushes the current for the positive half of the signal wave, and the other pulls the current for the negative half. Together, they create one strong, complete, and powerful output.
And there you have it. The signal has made it all the way through. So let's take a quick step back and look at the whole blueprint one more time.
So let's trace that path one last time. Stage 1, the input stage. It receives two signals and amplifies their difference. Stage 2, the intermediate stage. It boosts that gain even more. Stage 3, the level shift. It recenters the signal, gets it back to a 0-volt reference. And finally, Stage 4, the output stage. It delivers a strong signal with high current to get the job done. It's that simple. Listen, amplify, correct, and push.
When you look at it like this, you can see this beautiful symmetry to the whole thing, right? The op-amp starts with a high input resistance, so it can listen carefully without disturbing anything. And it ends with a very low output resistance, so it can speak powerfully and drive a load. Each stage has just one clear job, and they all build on each other perfectly.
So what started out as this mysterious black box is really just an incredibly elegant and logical system. These four stages just work together in perfect harmony, taking what might be just a whisper of a signal at the input and turning it into a powerful, commanding voice at the output.
And you know, that's the real magic here. An op-amp isn't just a component, it's a fundamental tool. Once you understand this four-stage blueprint, you understand the core of how to filter, amplify, and control signals. So the real question isn't, how does it work anymore? The question is, now that you have the blueprint, what could you build with?